Okay, so today's presentation is the thermal materials and coatings for near rectilinear halo orbit. Today's presenters are Abby Zinecker. She received a BS in Mechanical Engineering from the University of Houston and an MS in Aerospace Engineering from the University of Colorado Boulder. She has 2 years of experience as a thermal analyst from the Space Launch System and is currently employed by Jacobs working on the thermal design branch at NASA Johnson Space Center on Gateway, Passive Thermal, and Viper. Abby has been researching thermal control materials and coatings and optical property degradation for Gateway. Okay, they want me to read out the etiquette rules as well. I'll do that later. Okay, the second presenter is Sydney Taylor. She received a BS in Aeronautical and Astronautical Engineering from Purdue University and is currently a graduate pathways intern in the ES3 Thermal Design branch at NASA Johnson Space Center. She works on Viper, Gateway, FTRC, and Beam. Sydney is a PhD candidate in aerospace engineering at Arizona State University and is supported by a NASA Space Technology Research Fellowship. Her dissertation research focuses on VO2-based nanofabricated variable emittance coatings that provide temperature-dependent heat rejection. As a member of the Gateway Passive Thermal Control Team, Sydney has been investigating the optical property degradation of thermal control materials and coatings in the NRHO environment. Brittany Spivey received a BS in Mechanical Engineering from Texas A&M and is currently working towards her ME in Mechanical Engineering at the University of Houston. She has 2 years experience in the oil and gas industry. In May 2020, she became employed by HX5 Jacobs working for the thermal design branch at the NASA Johnson Space Center on Gateway Passive Thermal. Currently, her role has been assisting with the research for thermal control materials and optical property degradation, analyzing the effects of specularity of Gateway thermal control surfaces, and drafting a thermal control system data book for Gateway. Now, I'm just going to go over some of the conference attendee guidelines and etiquette. There are scheduled breaks. Please use those to check your phone and email. While you're in a session, please pay attention as you were in a room with speakers. If you are not registered for the conference but are attending, please register at the TFAWS website. During the presentation, please ask questions through the chat feature on the stream. The session moderator will ask your question if there's available time. If your question is not answered, please submit them to the TFAWS NASA email. Please include the presentation's title, author, and name. All right, Abby, you go ahead and start.
All right, can everyone hear me? Well, can you hear me, I guess?
Yes, we can.
Okay, great. All right, I'll go ahead and get started. So this is thermal materials and coatings for near rectilinear halo orbit, or NRHO. So you already got the little intro to all three of us, but they're obviously early career engineers at JSC in the thermal design branch working on the Gateway program. So today we're going to go over a little background of the optical properties, how they degrade, and the NRHO environment. And then we'll give a little introduction as why this is even important. Then we'll talk about the NRHO environment in a lot more detail, separated into natural and induced environment. And then Brittany's going to talk about some of the material options that we'll have out there. And then Sydney is going to talk about estimating end-of-life properties, conclusions in future work, and resources. So without further ado, the purpose of this research so far has been for Gateway. So the Gateway will be an outpost orbiting the moon that provides vital support for a sustainable long-term human return to the lunar surface, as well as a staging point for deep space exploration. It's a critical component of NASA's Artemis program. So future spacecraft visiting Gateway or Gateway itself in NRHO must withstand the space environment, and proper selection and placement of thermal control coatings is essential to the continued operation for the mission lifetime in NRHO. And if you're not really familiar with what NRHO looks like, I have two pictures here. The first one is in the moon-centered inertial frame. So if you can see my mouse, this is Earth. This is the moon right here. NRHO, or NRO, is this black orbit right here. So it's a very elliptical looking orbit. And then this picture over here, you can see what it looks like in the Earth-centered frame. It could be either this red one or green one. Both are technically NRHO looking orbits. Okay. So background, optical properties that we'll be talking about a lot today are IR emissivity, or mostly just called emissivity. It's the effectiveness in emitting energy as thermal radiation. And then solar absorptivity is the effectiveness of absorbing radiant solar energy. So why are they important? Spacecraft thermal control depends on optics of the material's surface. So some examples: high emissivity and low absorptivity typically make the best radiators. High solar absorptivity maximizes the heat load your surface will receive from the sun. So generally we want to reduce this because otherwise we'll get too hot. And then high IR emissivity maximizes how much energy you can output from your surface. And an A over E ratio, which is absorptivity over emissivity, helps determine how hot a surface will get in sunlight. And then all thermal radiation is classified as solar or IR. Solar energy is typically between 250 and 2500 nanometers wavelength, and everything else is classified as IR. So tuning of optical properties is an important tool for passive thermal management, but materials and optical coatings do degrade in the space environment. So your beginning of life is not going to be the same as your end of life, generally speaking. It depends on materials. So you can choose your materials and design which promote good performance during the lifetime of your mission. NRHO is a relatively unknown space environment. Since nothing has flown here before, we have to understand how this environment will affect degradation of materials and coatings. Most end-of-life data, or EOL data, is pertaining to low Earth orbit, LEO, or geostationary Earth orbit, which is different from us, and we'll show you why. So LEO, you'll have to deal with atomic oxygen, orbital debris, and then solar wind, vacuum, plume, micrometeoroids, and UV. Versus NRHO, you don't have atomic oxygen anymore, and you're probably not going to deal with any orbital debris. You still have the solar wind, although out here, since we're not protected by Earth's magnetic field, our solar wind is going to be much bigger deal than in LEO. But you still have vacuum, plume, micrometeoroids, UV, but you also have the addition of lunar dust and a lot more charged particles, since, again, you're not protected by the magnetic field. Now, in GEO, there's a little bit of orbital debris, not as much, but then you've got actually harsher charged particles in GEO than you do in NRHO, because GEO goes through the Van Allen belts, and NRHO, you're outside of that already. But you still have lunar dust in NRHO that you wouldn't experience in GEO. So now we're going to talk about the degradation sources in the NRHO environment in more detail. So these are separated into the natural environments and induced environments. So the natural includes UV, solar wind, galactic cosmic rays, or GCRs, and solar particle events, or SPEs. And then vacuum and micrometeoroids. So starting with UV, as I said before, this is the same as you'll get in LEO and GEO, because we're pretty much the same distance away from the sun, and that's a determinant in UV. So UV can cause darkening on surfaces, so an increase in absorptivity, and it will occur on surfaces that see the sun. So testing for UV, we can do ground testing. It's measured in equivalent solar hours, or ESH, which are the number of hours that the particular surface would be exposed to sunlight during the mission. Materials can be tested to the expected mission ESH on the ground. Unfortunately, that would take forever if we had to do it in real time, but 1 hour of ground testing can be equivalent to a maximum of 3 ESH. So for a 3-year mission, UV testing would take at least 1 year if you wanted to do the entire 3 years. The good thing about this is that UV damage usually kind of follows a curve, so it sort of flattens out the further down you go. So the longer you're up there, you get a little bit less damage. So most damage takes place earlier. But Gateway's mission lifetime is 15 years. So if we wanted to do the full UV testing for Gateway, it would be 5 years of testing. An important thing that we should know about UV testing is that it really should be done with the capability of measuring in vacuum, because exposure to oxygen causes bleaching, which negates some of the UV impacts. So you're not really measuring the same thing. And that's especially important for NRHO, because we don't have oxygen out there. Galactic cosmic rays, or GCRs, in solar particle events. These are, well, solar particle events come from the sun. Galactic cosmic rays come from everywhere else. They're both charged particle kind of things, sometimes like ions with high energy. And they're both kind of fluctuate with the solar cycle. But because they're high energy, they could mostly cause subsurface damage or pass through completely. So surface damage is what really matters for optical properties. So it doesn't really affect it that much. It could, but it's not as big a deal as the surface degradation, other sources. So it's mainly going to affect electronics and crew systems. You should definitely be worried about it, but for thermal surfaces, not so much. So it's not usually a factor for thermal material coatings. Now, solar wind. This is a continuous flow of mostly low energy charged particles from the sun. Since we're no longer protected by Earth's magnetic field in Leo, but radiation is not as harsh as in Geo, but we do have effects from solar wind in NRHO. These are low energy protons and electrons, so they're not able to penetrate into the spacecraft, but they do deposit energy on the surface, which causes darkening and therefore an increase in absorptivity. So testing for solar wind, what you do is you submit your material samples to expected energy levels and proton-electron fluence for the mission, and you determine the effects on optical properties. The timeline for testing on solar wind is more on the order of weeks, depending on your mission lifetime. It can be done at the same time as UV testing, though, depending on where you're having the test done. And then for NRHO, our energy levels and fluence tables are already provided in the SLS Spec 159, which is commonly known as the Disney, DSNE, if you're going to search for it. And you can find that on Google if you look. But you'll already find that some very helpful people have already done this research to determine what the radiation environment is like out there. But because of all this radiation and charged particles, it's definitely important to have electrically dissipative surfaces to reduce the risk of electrostatic discharge, or ESD events. Important takeaway from this. Now, we can't ignore the magnetotail. The magnetotail is a broad, elongated extension of the Earth's magnetosphere on the side away from the sun. And you can see sort of in this picture, we have the moon's orbit. And basically, we're going to be following this line in NRHO. And you're going to pass through the Earth's magnetotail every 27 days or so. And transit lasts about 6 days. So what happens in the magnetotail? This is where relativistic electrons, due to magnetotail magnetic reconnection, it's kind of like the wind is whipping really hard with radiation and charged particles. You could have bow shock, you have increased solar wind density interspersed with decreased solar wind density. So you'll have shells of higher proton fluence with lower density in between. It's kind of a wild environment. Luckily, it's already been included in those calculations that are shown in the Disney document I mentioned before. So the size of the magnetotail at lunar distance, some researchers kind of vary on this, but it looks like it's between 10 and 35 Earth diameters. So in NRHO, we're going to pass through this. It's something to keep in mind. So vacuum, that's present everywhere, not unique to NRHO. So vacuum exposure causes outgassing and contamination. That's the real worry about vacuum. Outgassing is the release of gas that was trapped inside a solid. Then these outgas products can recondense on external surfaces, causing contamination of the surface, which can affect optical properties, sometimes a lot. So the outgas product can be ionized by solar UV and then electrostatically reattracted to the vehicle. So there's a couple different ways that it can condense and cause contamination. In NRHO, we have a little bit of difference between LEO as far as contamination is concerned, because the solar wind is not as effective at carrying away particles from the surface as atmosphere, which would be present in LEO, so like atomic oxygen. That kind of pulls away some of these particles that would otherwise be condensed in LEO. So in NRHO, we're kind of expecting contamination to be worse than LEO. So depending on how bad this is, we don't know yet. We haven't been there yet. But contamination could be a significant source of degradation in NRHO. So generally, outgassing is mitigated by design or material choice. So first of all, you can choose materials that are low outgassing, even if a material is low outgassing though, quote low outgassing, if there's still a large quantity, it can still cause problems. Also, there are just some materials that tend to outgas a lot more than others. So try and choose lower ones. The next option is to limit line of sight. So you can do this by arranging your surfaces or contamination sensitive surfaces so they're not within line of sight of those higher outgassing surfaces. So keep them from facing each other. And when I say contamination sensitive surfaces, those are generally radiators, anything that has a really low absorptivity that you don't want to get increased. So radiators are the big ones there. So some of the things that you can look at when talking about outgassing of your materials, there's the total mass loss, or TML, of less than 1% is standard, and that's confirmed with a vacuum stability test. There's also collected volatile condensable materials, or CVCM. This is the standard amount that might recondense on a surface, and it's limited to about 0.1%. And then ASTM E1559 is a more sophisticated test that estimates contamination on sensitive surfaces. So micrometeoroids. The Earth and Moon encounter approximately the same population of meteoroids. Obviously, the gravity and size of the Earth and Moon affect the local environment around there. There's the meteoroid engineering model, or MEM3, which predicts the meteoroid flux and includes the NRHO environment. So this work has already been done for NRHO, and you can find it in the Disney too. So luckily, there's a lot of stuff that's already in there. Meteoroid directionality is not random. The flux will be different depending on the direction the spacecraft is facing. So you'll have to do evaluations for your own spacecraft to determine where you will probably have the most impact from meteoroids. One thing to note is NRHO doesn't have the luxury of radar tracking for large micrometeoroids like we do in LEO, so it can't be just avoided like the ISS. There is a potential to punch holes in solar cells or radiators due to micrometeoroids. It's kind of unlikely to be significant for thermal surfaces, just because there's nothing you can really do about it, and it doesn't typically affect optical properties that much. So it won't affect your selection of material for the most part, but it may affect performance over time, just for thermal coatings as far as that goes. Other materials it probably does affect. And then there's synergistic effects. So this is sort of when those different effects combine. So a couple examples. I already talked a little bit about UV and atomic oxygen combined on certain surfaces such as beta cloth have a canceling effect known as atomic oxygen or AO scrubbing. With only UV, beta cloth will yellow and absorptivity will increase. If you add atomic oxygen, that will sort of scrub away some of that yellowing, and your absorptivity isn't quite as bad as it would be with just UV. There's lots of data out there already for UV only effects, so this can still be used, but you do have to make sure that in your test or in whatever research you're looking at, that the absorptivity was measured in vacuum to make sure that there was no oxygen exposure. Then there's also UV charged particles. They can have some interaction. It's material dependent. It's called photolytic deposition, which is kind of a chemical decomposition caused by light or electromagnetic radiation. And then there's also the effect of enhanced outgassing and contamination due to spacecraft charging and UV. So if you have a surface charge on your spacecraft due to the plasma environment, which we would have, this is like solar wind causes this. It could, when you have outgassed products and they start to float away, then you have solar UV impacts that and causes it to ionize. So instead of being repelled by a vehicle, by the charged vehicle, it could be reattracted instead, and then you have more contamination. So that's one way. There's also just the fact that the hotter the surface is, you could also just increase the amount that you're outgassing. So there's that. Okay, now for the induced environments. You can have plume impingement, venting, foreign object debris or FOD, lunar dust, and crew interaction. So when I say induced, I mean this is not something that's already present in the environment. It's something you're bringing with you. So for plume ejecta, plumes from engines or spacecraft or visiting vehicles can cause contamination that damage optical properties. And there's a few ways that the plume can do this. First of all, there's just straight up residue buildup on the surface could cause contamination. Then there's chemical reactions that could occur on the surface due to partially reacted products from the plume. And then there's erosion. It can cause like a sandblasting effect. Could be relatively small, probably within the noise or margin that you have on your material optical properties. So generally, this is mitigated by design. just try and arrange your plumes so they're not impinging on contamination sensitive surfaces, which again are radiators or solar panels maybe. Venting. So depending on your spacecraft, you could have venting, for example, vented air from the airlock or vented gaseous or liquid wastes. Gases will likely dissipate depending. Water-based liquids could be more of a problem, especially if they have dissolved substances in them. Contaminants on the surface facing the sun may just get baked off, but not necessarily on the space-facing side. And then particulates and foreign object debris, or FOD. This could be brought from Earth or caused by damage to the spacecraft in orbit. For example, if you have a surface that's painted, it could flake off, or there's dust or something like that. That could cause an increase in absorptivity, generally. Now, lunar dust. So I wanted to note here that lunar dust may be found in the natural NRHO environment as well. And I have more details on this if you're interested in the backup charts. But since in the induced environment, the effects are greater unknown, so I wanted to focus on that here. It's unknown how lunar dust in orbit will be affected by the lander and other surface activities. So when you send a lander to the moon, it kicks up a bunch of dust, which could be kicked up all the way into NRHO after lunar landings, and kind of the same for ascent. That also causes a big dust plume from the surface. Also, lunar dust could be brought back to NRHO via an ascent vehicle. We don't know how dust would transfer from one surface to the next. We don't know how much dust would stick to the ascent vehicle and survive launch. There's just a lot of unknowns there. So we don't know how lunar dust might adhere to thermal surfaces or how it might impact thermal performance. We have some past information on this, but I'll go into that. So it could adhere and obscure the surface, which would degrade the thermal performance by degrading optical properties, or it could also just be a dust layer on the surface and provide thermal insulation. It could also abrade the surface and damage optics that way. So some surfaces, some instruments on Apollo 16 and 17 showed degraded heat rejection capabilities due to dust coverage and subsequent overheating. So we have experienced this before on the surface. We had, I think, a couple of failures actually on like battery radiator heat rejection. So it's unknown if the percent coverage on surfaces in NRHO would be 0.01% or more. We have some research that showed that just a 12% dust coverage on a Z93 radiator is estimated to increase alpha by 50%. That would be a huge detriment. But again, it's very difficult to predict coverage at this time. It would be dependent on the type of dust, the size distribution of the particles, the shape of the particles, and so many other things. So this is definitely a topic that we're interested in more research. Another thing, crew interaction. So depending on your mission, if you are required to have EVAs, astronauts can cause damage to external surfaces during an EVA. So adding this capability adds several requirements for your material selection due to like astronaut safety. For example, you want to reduce sharp edges, hazardous materials, things like that, so that astronauts are not endangered when they're doing an EVA. And then there's also the touch temperature that you have to maintain that's safe for them to touch through their gloves and boots and stuff. So that's your A/E ratio coming into play. You also have to have more durable materials when the astronauts, or if astronauts are going to come in contact with your surface. So it will have to withstand kick loads, peeling and delamination. You'll have to make sure that your insulating blankets or MLI won't tear if an astronaut comes in contact with it. So flaking or shattering of a surface could cause particulate, which can lead to further damage to the surfaces themselves, or also other mechanisms on your spacecraft or the spacesuits. Could also result in sharp edges, which we already talked about is a safety hazard. Another thing, you'll have to deal with visibility of your surfaces if an astronaut will have to use it. For example, we have colored handrails that we usually use for the translation path. We usually have gold anodized aluminum handrails, so they're very visible for the astronauts to use. There's also labeling you have to take into account. So even your labels, you can't just stick a sticker on there. They have to be able to withstand the space environment and not degrade over time. There's also specularity or glint requirements that could interfere with the astronaut's vision. So an astronaut won't be blinded by a really shiny silver blanket while they're trying to work. Okay, now if we have any questions on the environment section, I can answer them here.
Okay, we'll just give them a couple of seconds.
I think I see one in the chat, actually. For UV degradation, you mentioned an asymptotic curve, higher degradation early, low degradation later. What time duration should be considered high degradation versus steady low degradation? So this is pretty material dependent, of course. And honestly, I think part of the problem there is because if you have a surface that starts off with a really low absorptivity, then it's going to degrade faster, and it's going to degrade more. But it depends on the material. So sometimes you'll see something that like it degrades a lot over the first 6 months, or it degrades a lot over the first couple of years. It depends on the material, and you'll have to look up for your specific material, I think. So there's that question. Was there anything else? It is a question if during the 6 days of transit, you mean transit across the sun and solar flux density, right? 14 and 15. 14 and 15. 6 days of transit. I think we might be talking about this slide. So this, I'm talking about transit through the magnetotail. So if you're taking, well, the moon takes, like 27 days to orbit, then 6 of those days is in this range while you're passing through the magnetotail. So that's what I mean by transit. I'll talk about materials more, or Brittany will talk about materials more in a minute. What degradation information do you have about ejected crew materials, human waste, etc.? I actually don't have any information on that so much. It's mostly avoided by design of your spacecraft. So you basically have to aim your vents so they're not facing sensitive surfaces. But it is something that I'd be interested in hearing more about. That's something that we plan on looking into more after this, because we're still trucking along on this problem. So I think that's all the questions for now. So I'm gonna go ahead and move on to material options. So I'm gonna go on mute and let Brittany.
Thanks, Abby. Okay, so I'm going to be going through in this section, I'll be discussing the different material options for the different materials on the spacecraft. You can go to the next slide. So we'll be talking about some different materials. You'll see some, we'll talk about solar arrays, radiators, MLI, structure, and then cameras, star trackers, and windows are actually going to be considered more in our future research. There's still some unknowns surrounding those. So you'll see those are actually in our future work plans. You can go to the next slide. So we'll start with the solar arrays. So degradation on solar arrays is primarily due to radiation. Ultimately, the power team, though, should have a profile of power loss versus the time. Degradation also occurs due to UV photolytic deposition. UV photolytic deposition is when UV causes a chemical reaction with contaminants on the surface. Another form of degradation is lunar dust, but as mentioned before, impacts are still going to be unknown for this application. And then typically solar cells do run warm. So for the materials for solar arrays, a cover glass is used that is very stable. The first one is a fused silica, which actually has a greater resistance to darkening by UV and electron radiation. And the other is microsheet glass, which is a cerium doped borosilicate cover glass. This is used on thinner areas. It's not as fragile, but it is susceptible to UV radiation. But this is also directly related to its cerium doping. So ultimately, though, solar cells vary widely by the manufacturer. So there will be different thermal and optical properties chosen based on the environment or application. Next slide, please. So next we'll go through some different radiator options. The first one we'll discuss is the optical solar reflectors, or OSR. OSR is a second surface mirror. It's cover glass made of quartz over a metallized reflecting layer. This metallized reflecting layer is going to be most commonly aluminum, silver, or gold. Just some characteristics of those reflecting layers. So aluminum is going to be the most resilient material, and it does have good optical properties. Next is silver. It is the best reflector, but susceptible to atomic oxygen degradation. And then gold is going to be the least used option, though, because of its relatively high absorptivity. So you'll see most OSRs have a high emissivity and low absorptivity. Emissivity value is about 0.8, and absorptivity is very low, as mentioned. It's going to be around 0.08 to 0.13. Ultimately, the lowest absorptivity emissivity ratio of all options will have the most favorable performance, though. So OSRs are very stable to most degradation sources, but they are susceptible to contamination. They are also delicate and require experienced processing. They're limited to flat surfaces, and they're also expensive and heavy. There's also another option out there made by Creo, which is a newer thin film, and it's a flexible version that may be an option. It's applicable directly onto spacecraft external surfaces. Although degradation will likely be affected, though, so it will eventually require testing. Next slide, please. So the next option for radiators is white paint. The emissivity value of white paint is about 0.89, again, very high to 0.94, while the absorptivity is very low at about 0.2. White paint is going to be sensitive to different things such as UV, solar wind, and contamination. There's 2 different coatings that will go on this white paint. And so the first one is the silicone coating. This has potential outgassing problems as well as higher degradation due to radiation. It is easy to apply though because it's a smooth paint and it's fairly durable and rugged. So example of this is Alion DS13 used by JPL as well as Abtec 2719. Both of these are electrically dissipative coatings, or paint, sorry. The next coating is a silicate coating. This one is going to be more difficult to apply than the silicone coatings, but it is stable, reliable, and it does stick to most of the hardware. Another example of these is Alion C93 C55 and Abtec 2711, which again are both electrically dissipative. Although with Abtec 2711, currently there's no radiation or solar wind testing yet. Next slide, please. So the next option for radiators, material option is going to be silver Teflon with ITO. This material option does have lower performance than optical solar reflectors and as well as some white paints. It is used frequently in LEO though. As you can see on the left, it's used on Hubble, it's also used on Shuttle, and many more. It is lightweight and low cost, although it does degrade in radiation, and it does tend to peel under thermal cycling and atomic oxygen conditions. The ITO, the Indian tin oxide, is a optically transparent coating that's electrically dissipative. ITO is also going to be delicate and it can rub off easily. So there are going to be some issues where the verification of the continuous ITO film layer is going to be difficult. Next slide. The next material option for radiators is an oxide composite system. This will have a lower emissivity as compared to OSRs and white paints at about 0.6 to 0.7. It is more stable than Teflon though, especially from UV and solar wind. It does use silver and aluminum or aluminum as a reflective layer, which is vapor deposited on the hardware or films. And its thickness runs about 2.5 to 2.6 microns total. 2.3 of those are oxides. And it is fabricated through an electron beam evaporation. This material option can be applied to non-planar surfaces, although eventually its surface roughness will affect its absorptivity. And then again, it may need an additional coating to meet an electrical dissipation requirement. Next slide, please. So the next material we'll be discussing is multi-layer insulation, or MLI. MLI is going to be a material that uses many layers of low emissivity films as heat transfer barriers. The purpose of this is to minimize radiation through adding a reflective layer, as well as minimizing conduction through reducing the contact between layers. It does provide micrometeoroid protection, atomic oxygen protection, as well as plume impingement protection. Next slide. So there's many different layers to the MLI. So there's going to be the outer layer, separators, interior layers, as well as the inner layers. So what I'm going to discuss first is the MLI outer layers. So the nominal materials used are going to be silver Teflon and aluminized Kapton. So silver Teflon has a very low absorptivity to emissivity ratio. Although Teflon does lose its mechanical strength over time, and it should ultimately be backed with Kapton or beta cloth. Aluminized Kapton is going to be another nominal material. It's lightweight, it's relatively delicate, and it generates particulates. The next material is beta cloth. It offers atomic oxygen resistance, it's durable, and it has MMOD protection, offers MMOD protection. Although it is heavy and it does see substantial degradation, This material can end up turning black over several years in geo. Although atomic oxygen does cause a bleaching effect, which will counteract the darkening from the UV and contamination. But again, this is in Leo. So the next material is germanium black captain, or GBK. This material is electrically dissipative and it minimizes glint. It does degrade quickly in storage due to handling, though. The next material is stamite, which is similar to GBK, but it does have a better ground handling performance. And the last is astroquartz. It offers high temperature resistance, durability, and then MMOD protection, although it is heavy. So just a note, ITO, the Indian tin oxide coating, can be applied over other surfaces such as the silver Teflon to improve the charge dissipation as needed. Next slide, please. So as mentioned, the other layers, there's interior layers, there's separators, and there's also an inner layer. So for the interior layers, it's often, the material that's often used is aluminized, silvered, or goldized, Kapton, mylar, polyester, Teflon, or Kevlar. Some notes, goldized is going to be ultimately more expensive, but it does have a lower emissivity. Mylar is actually going to be the most common, but it should not be used over 250 degrees C, and it also is a flammable material. And then Kevlar is used for MMOD protection, and then Teflon is used when a very low absorptivity to emissivity ratio is needed. For the separator layers, you'll see materials such as Dacron, Nomex, nylon, silk, tissue glass, Dexiglass, and astroquartz. As a side note, astroquartz is going to be best used for the higher temperatures. In the inner layer, you'll see materials such as Kapton, reinforced with aramid, laminated Nomex, Kevlar, or it could be the same materials as the interior layers. Just a takeaway, so the low emissivity coating used most for interior layers is going to be aluminum. It doesn't tarnish like silver, and it also is relatively inexpensive, and it is available in a variety of thicknesses as well as base materials. Next slide, please. Okay, so next we're going to discuss the materials on the structure. So most of the surfaces will end up being covered by radiators or MLI, but not all. So for example, in ISS, this was usually anodized aluminum, where the surfaces had to last for 30 years without refurbishment. Examples of this is on the truss, electronic boxes, and handrails. And this is going to be resistant to atomic oxygen. So a rule of thumb is that in a location where a predictable temperature is critical, you could use a material with a static or predictable absorptivity to emissivity ratio of 1, and then design around it. So many coatings actually do provide this property. It's not optimized though, but it could be relatively stable over the lifetime. For example, one of these is a black coating, like polyurethane aeroglaze Z307. ISS used black surface coating, which was black anodized, on the pressure mating adapter to provide predictable temperature, which is also important for docking. So. Next slide, please. So just some materials used on structure. The first one is bare aluminum, and I'll go through some of the characteristics with these materials. So the first one is bare aluminum. This material does tend to get hot in the sun exposure and ultimately would need some sort of corrosion protection. The next one is anodized aluminum. This absorptivity to emissivity ratio is less than 1, which means it could meet temperature requirements. Anodized aluminum is not electrically dissipative, but you could add ITO to the surface to meet that requirement. It also is not generally recommended for open, large areas. Its optical properties vary widely due to processing, but it can be customized for each application. And then generally, aluminum oxide coating does not outgas, but a colored anodize could, depending on the processing. The next is iodine iodide conversion coating. This provides corrosion protection. It is more conductive than anodized, and although it is not going to be scratch resistant. The next one is polyurethanes and silicone coatings or paints. These would end up changing color and increasing absorptivity over the lifetime, though. The absorptivity emissivity ratio would probably not increase over 0.75 at end of life. Again, on this one, you could use an electrically dissipative coating. The next material is primers. Primers are used to provide some protection. They do end up making other coatings adhere better, and again, could be electrically dissipative. And finally, we have composite structures. These can fly without any coating on them, obviously depending on thermal requirements. Some coatings don't really adhere well to the composites though, especially with temperature cycling. Next slide, please. And finally, we have EVA path. So EVA is included in the design and many different requirements. As mentioned before with Abby's presentation, it's for the safety of the astronauts as well as different spacecraft performance, and making sure that it's not reduced by the crew interaction. So just some notes on different EVA path materials. So first we have OSRs. There's a concern with OSRs taking a kick load and becoming sharp edges if damaged. Next, we have white paint. This is also have concerns around it because it can sometimes flake due to handling. Even a brush by an astronaut could cause damage to the surface, which could ultimately contaminate other surfaces or impede mechanisms. The next one, there's with the silver Teflon ITO, there's a moderate concern that it also could be brushed off by the crew member as well. With anodized aluminum, this is a good material and it has well-controlled properties. And when coated with ITO, could be a good option for the EVA paths in NRHO. And then next we have handrails on the EVA translation path, which are usually going to be gold anodized for the visibility. And then lastly, we have MLI. There is going to be a concern with MLI tearing due to crew interaction. So ultimately, one would need to consider using more durable materials such as beta cloth or astroquartz for this. And that concludes the material section. And
if anybody has any questions on the materials section, you can ask them now and hopefully we'll see them in our chat. On embossed films instead of separation layers, if you have experience or data, can you comment on what performance difference or other considerations there may be? Okay, well, I can give a little background on this for those of you who don't know. So you have, let's look at MLI a little bit. So you have these interior layers with separators in the MLI. So sometimes you may not want to use a separator or you may not need one. So you could emboss the interior layers instead. So it makes them sort of bumpy so they don't touch each other as much, which is basically the whole point of a separator. So you could just emboss them instead. Now, as far as your actual question, can I comment on what performance difference? No, I haven't looked at that yet. It's definitely something I can add to my to-do list though. Other considerations, well, certainly there's a weight consideration. If you take out the separators and emboss your layers instead, you would save some weight on separator materials. There could also be a chance that you have higher conduction through the layers though, because there are maybe more points of contact than there would be with using an actual separator. So there's probably a give and take there. Why do you need to prevent bare aluminum from corroding? That's a good question. So for ground effects, there could be some corrosion on the ground. For bare aluminum, there could also be corrosion in space from aluminum due to the contaminants that we are expecting. There could be lunar dust, there could be outgassing contaminants, plume contaminants especially could corrode bare aluminum. But yeah, corrosion is always something that is looked at, corrosion protection. That's just what I've heard. I'm a young engineer just learning about this too, so I've always been warned about bare aluminum corroding. So that's any other questions? Materials.
Abby, this is Sydney. This is just a comment on the bare aluminum corroding. I think a big part of that is also in the ground case, because if you have just regular aluminum and it's on the ground, then it will oxidize over time, and then that oxide layer can decrease your emissivity. So that might be one consideration.
Yes, exactly. Because all of your surfaces will have to withstand the ground and transit environment before we even get to NRHO. So things like handling or sitting in storage also affect your beginning of life properties. Does cost data exist, and is cost considered in material selection, where cost is defined as either dollars or schedule required to apply procedure? For example, a material with an 18th month lead time and cost $3 signs per meter squared seems less useful than a cheaper material. I would say people other than thermal engineers probably care a whole lot more about cost. And we did mention a little bit in here that OSRs are one of the more expensive options, but they have really the best radiator material properties. So they're more expensive, they're heavy, there's a lot of downsides, but they're really good radiators. They do cost a lot more. And there's some that are cheaper, like silver Teflon, but silver Teflon also has not as good performance, and it has some degradation issues that we talked about. As far as lead time goes, there are definitely some that are easier to apply, like white paints or something. Those are great. And you can get a variety of costs on white paint. So yes, there's definitely some cost considerations. I don't go over them quite that much because I'm a thermal engineer, not a budgets person, but definitely there are some costs considered in your material selection. How is the inner layer of the MLI blanket typically fixed to the spacecraft surface, and what practices are taken to ensure it doesn't become attached? So some options that you can use to attach your blanket are my personal favorite, Velcro. You can also attach it with adhesives or tapes, things like that. So how are measures taken to ensure it doesn't become detached? I guess for adhesives, at least, one example would be you have temperature requirements for that adhesive. So you'd want to make sure that you do your proper analysis to ensure that your adhesive won't become too hot or too cold. Usually it's behind an MLI blanket. It should be pretty good, but something that you need to take into account. And then for MLI, or maybe you would have some movement issues that you're concerned about. Like you have a mechanical part that's moving around and you want to make sure that your MLI doesn't tear. that would be built into the MLI structure. So you might have a baggier blanket than you need in one position, just because it, if you want the full range of motion, you have to make your blanket expand to fit that. So I would say a baggy blanket surface would help to make sure that it doesn't rip or become detached from the spacecraft. Hopefully that answered a little bit of your question. Anything else? Inner layers are sewn together. Yes. So you can use thread or you can use tape to keep your inner layers together. There's a couple different options. So a note on the thread. You want to make sure that your thread, since it goes all the way to the outer layer, you have to make sure that your thread is also going to be able to withstand the space environment. And sometimes your thread might be one of those materials that is high outgassing. So you have to make sure that you keep that down. Another thing on threads is sometimes they're susceptible to atomic oxygen degradation. And no matter what we say about NRHO not having atomic oxygen, we have to get to NRHO somehow, and it's going to go through LEO, which has atomic oxygen. So we have to make sure that all of our materials can withstand however long we're going through that transit phase as well. So yes, sewn together with thread. On aluminum coatings, do you look at electrolysis nickel plating? I'm not sure about this. Sydney, do you know about this?
No, I'm not too familiar with that.
So that's a no, but we will, I'll make a note of that. Any other questions?
I think typically for aluminum coatings, you just use some vapor deposition technique, you know, like aluminum or electron evaporation or sputtering or something like that.
What kind of materials do you recommend for a structure of a CubeSat orbiting in the thermosphere? I have no idea. I would have to look that up. Anything from Sydney or Brittany on that question? I say a good choice for structure is always anodized aluminum. It's one of my favorites. One thing I want to talk about anodized aluminum, though, that maybe didn't go through all the way, is that the optical properties of anodized aluminum can vary really widely depending on your processing. And anodized aluminum is used for a whole bunch of applications other than space. And so most companies who deal with anodized aluminum are not used to caring so much about their optical properties. So when you go to a company and say you want anodized aluminum, and then you want the optical properties to be repeatable and well known, that's something that you have to talk to the processor, or talk to them about their processing. So make sure that they have all of the things that they need to ensure that their optical properties are going to be the same and they're going to be what they say they are. Yep, there's lots of different options that you could think about for a CubeSat. Any of these options except probably composite. I would expect that your CubeSat is probably aluminum to start, but you could use anodized aluminum, you could do iodine or iridite. You could do a primer or just a primer or a primer and paint, because primers increase the adhesion of paints and things like that. Yeah, so hope that answered your question, at least helps. Anything else? If not, we will start talking about end-of-life properties and estimation of end-of-life properties. So Sydney?
All right, awesome. All right, thank you, Abby. So I'm Sydney, and I'll be talking about the end-of-life property estimation for optical degradation. So next slide, please. So the estimating of end-of-life optical properties involves kind of a step-by-step process. So first you'll start with your BOL, beginning of life absorptivity and emissivity. So this may include some ground handling effects, as we were talking about earlier, but it also may not. It kind of depends on the nature of your mission and the materials you're working with. So you'll start with this beginning of life absorptivity and emissivity. And then the first thing you'll consider is the measurement uncertainty. So when you take measurements for the absorptivity and emissivity, there's some amount of measurement uncertainty, just as there is with any measurement. So generally about 0.02 is what we'll see for the measurement uncertainty for absorptivity and emissivity. And then the other thing to consider is also that there might be some uncertainties in your thickness. So the optical properties of your coating will depend in some part on the thickness, so there's some uncertainties involved with that. So once you can accommodate your uncertainties, the next thing you'll want to think about is for your specific environment, what degradation factors are present and which ones do you expect to have an effect. So of course, this whole course is talking about degradation in NRHO. So as Brittany and Abby have both identified, one of the primary factors in NRHO is solar wind over the lifetime of the mission. So what you'll do is you can do some testing to determine what the degradation is expected for solar wind. So you'll get some fluence values and some energy values from your environments team, and you'll test your materials according to those values. And then you'll get a delta for your emissivity and a delta for your absorptivity. And then you'll do that for each of the different factors. So another factor that's expected to have a big impact for NRHO is UV, again, over the lifetime. So you'll want to test, do UV testing for each of your materials that you're considering. And one thing that's important with this testing is to do that in vacuum, as Abby mentioned. If you do the measurement after and you do it in air, then you'll get some bleaching effects, which will suggest that your absorptivity is much better than it actually is in vacuum. And then another thing just to consider also is that UV is not expected to be very different from LEO and GEO, so you can leverage some of the existing test data from that. So in addition to the environmental effects like solar wind and UV, you also have the degradation from contamination that you'll need to take into account. And this can be difficult to quantify just because not only do you need to understand which contaminants you have, you also need to understand where is your surface relative to those contaminants. So that's going to be really dependent on your design. So you'll need to think about the line of sight between your surface and your outgassing materials, or thrusters, or if you're in the view of the sun, that could potentially be worse due to the synergistic effects that we mentioned earlier. So you'll have to develop some testing conditions based on your design and what you know about contaminants that are involved in your spacecraft, and then you'll evaluate the results of that based on your requirements. So you'll be able to come up with a delta that you expect for your contamination to add that basically to the degradation you expect for your end-of-life properties. So some other important things to think about is that it's not just the degradation that you'll see in your environment that you're targeting, it's also going to be the degradation that you'll experience in transit to that environment. So one thing for NRHO is that even though we don't have atomic oxygen in NRHO, we will have atomic oxygen on the way to NRHO. So we'll need to assess, will the time that we're in low Earth orbit be long enough to see atomic oxygen damage? And then if we think it will be, then you'll have to do some testing to determine what degradation effects we're going to see from that. So then the last thing you'll want to consider is that so far we've been talking about doing this step by step. So you take for that particular factor, what degradation do you expect to see? But just be aware that there's some synergistic effects as well. So for an example, we were talking about UV, AO, and contamination. If they work together, then you might see some different results than if you consider each of them separately. So that's just something to be aware of. So on the right hand of the slide, we have a figure that basically shows, first on the bottom, you have the beginning of life absorptance as an example, but it works the same way for the emittance. And then you add each of the degradation factors and the effect of those. And then at the very top, you can see you have your end of life absorptance or emittance. So next slide, please. Oh, no, thank you. So what we have on this chart is an example of the charts that the Goddard Contamination and Coatings Engineering branch uses to assess what the end-of-life absorptivity and emissivity are for various coatings. So you'll see they do, like we just discussed, it'll say what is your measurement uncertainty, what are the degradation factors, the environmental ones, and what is the delta associated with that. And then finally, what is the delta associated with the contamination? So next slide, please. So here we did an example for Z93C55. So this is a conductive white paint that's of interest for Gateway. So you'll see that we started with the beginning of life absorptivity and the emissivity, and then we went through and just added up. So for an example, what was the measurement uncertainty, the thickness of the coating and uncertainty related to that. And then we went through for the UV, the solar wind, outgassing, venting, EVAs, and lunar dust. So we added up all the deltas, and then you can arrive at the end of life properties. So in this particular example, we got 0.397 for the absorptivity, and then we got 0.885 for the emissivity. So one thing that's really important to think about is that since we haven't done a lot of testing for NRHO, and as Abby has mentioned, the environment is quite different, you know, the NEO and GEO, most of these values are derived from a literature study. So it's important to verify the end-of-life properties with proper testing. Next slide, please. So here we have a chart that describes some of the requirements besides just the optical property degradation that you'll want to think about as you're selecting coatings. So we have the absorptivity and the emissivity for the coating, but there's some other important factors such as the specularity, whether it's electrically dissipative, what it's sensitive to in terms of degradation, whether you can use it on the EVA path, or also has it been used before and what has it been used on. So we've listed some of the pretty typical radiator coatings, like Z93 has been used pretty prolifically on, like say, ISS and several other missions. And then similarly with silver Teflon, it's been used pretty substantially. And then you have some other examples that have also been used. So for an example, if the environment that you're working in requires an electrically dissipative coating, then even though like some of the white paints might have very good properties, you can't use them because you won't meet your electrical dissipation requirements. Whereas, for an example, another requirement might be if you're looking for materials for the EVA path, then there's some requirements you might have in terms of you can or cannot use a particular type of coating. So for Gateway, we have a requirement that you cannot use white paint on the EVA path. So that has to factor into your decision making as well. So just two notes that are kind of important. One is that you'll notice a lot of times people will use AZ93 and Z93 interchangeably. So they're actually distinct formulations, and AZ93 is made by AZ Technology. And then Z93 was another formulation that was made prior than that, and I think it was made in academia. So those are distinct coatings. And then the second note just to make is that a lot of these coatings intrinsically don't meet the electrically dissipated requirement, but they can be made to by adding an ITO top thin film. So these are for radiator coatings. So if you go to the next slide, we'll talk about MLI coatings as well, or MLI materials. So just as you do with the radiator coatings, it's also important with the MLI coatings to think about your requirements. So some requirements that might be important are, for an example, temperature stability. So if you have an application where you have very high temperature, then as Brittany mentioned, there's a lot of materials that won't work at high temperatures and they'll melt, for an example. So you want to consider using a material such as astroquartz that is stable at high temperatures. And again, you have the same requirement with electrically dissipative, so you'll have to think about what coatings you can, or what materials you can use in your MLI that will be electrically dissipative. Another thing to think about too is what factors are sensitive to. For an example, GBK is sensitive to ground handling, so that might also be consideration of factors into your judgment. But the idea of this chart is just to give an idea that even though a coating or a material might have very good optical properties, there's other factors that might be equally as important when you're selecting coatings. So it's important to be aware of your requirements so that way you're not selecting materials that, although they might look good optical property-wise, won't actually meet your requirements. Next slide, Abby. So some other requirements or impacts to material choice that we didn't include in the charts were an important one is touch temperatures. So if your surface gets very hot, you have some requirements in terms of the crew for touch temperatures. So that's something to think about. Another one is temperature stability. So if your application has you working at very high or very low temperatures, there's some materials that won't be stable at those temperatures. And then also you have the same thing with thermal cycling. And that's not just the material itself. It can also be how the material adheres to its substrate. So there's some materials that if you cycle them, or if they're at very cold temperatures, then they might delaminate from their substrate. And obviously that's not ideal. So then the next factor you can think about also is durability. So that'll be things like kick loads. So if like if astronauts say impacts your radiator, right, that might have some bad effect on it if it's, say, something that's more fragile like an OSR. Same thing with the micrometeoroids, where you might be able to damage it depending on the material that you're using. So those are factors to take into consideration. As I mentioned before, you want to think about your transit environment. So you might be encountering a space degradation effect in your transit environment that you're not in your final environment. Ground exposure is also important. If your spacecraft is, sitting in storage or sitting, somewhere where it's exposed to corrosion or moisture or something like that, then that might degrade your properties before you even leave Earth. So that's something that you really need to take into consideration. Also, hazardous materials, you might have some requirements or some desires from your mission not to use certain materials because they're hazardous. Another thing to think about is particulate generation. And then finally, there's some requirements also for certain elements of your spacecraft. For an example, we've talked about the handrails or with labeling where they have to be a specific color. So that's a requirement that you don't really have a choice in, and you have to design to that requirement. Thank you. Next slide, please. Okay, so in summary, so the NRHO environment shares some similarities to LEO and GEO, but there's also some significant differences that cause materials to degrade differently. So whatever material or coating you select will have to withstand the NRHO environment, and then will experience optical property degradation due to UV, solar wind, vacuum, micrometeoroids, potentially lunar dust, venting, crew interaction, all of those. So you have to have an understanding of what space environment effects you'll be encountering. So then another thing to consider also is that some of the severe degradation effects will be dependent on your spacecraft design, but then there's others that will be expected to be pretty significant that you can account for just generally with testing. So like UV, solar wind, et cetera. So then another thing to think about, and I've mentioned this, is that your materials and coatings should be selected by your thermal optical properties, but also you want to make sure that they meet your requirements as well. And then finally, you should design your spacecraft such that you're limiting the contamination by either orienting your sensitive surfaces away from higher outgassing sources, plumes, vents, or configuring your spacecraft in a way where it's not being as exposed to the degrading factor as it could be. And then finally, to be able to get your end-of-life properties for NRHO, you can estimate that on the ground using that step-by-step process that I described, and then you just add some margin. So that way you can do your thermal analysis. Next slide, Abby. So for the forward work for our project, we're going to continue researching the NRHO appropriate materials, and we'll do that for the camera start trackers and windows. And then we'll also continue to estimate the end-of-life properties for the coatings that we're interested in. For an example, the Z93 C55. One thing that's really critical is that we want to test the materials and coatings to understand the end-of-life properties. So we can estimate it based on the literature, but because there's not testing that's been done for NRHO before, it's really critical to validate our assumptions with testing. So that can include the ground testing, so like solar wind, lunar dust, et cetera. Or it can also include in situ testing for lunar dust contamination, et cetera. Next slide, Abby. So finally, we had the opportunity to talk to a lot of experts while we've been doing this project, and we've also received good support from our thermal design branch, ES3. So we'd like to thank Ron Lewis and Scott Coughlin, their ES3 management. And then we'd also like to thank Lori Carrillo, who's our team lead for Gateway PTCS. Eric Malroy is the PTCS lead for Halo. We also received a lot of help from folks in the ES4 Materials and Processes branch. So like Erica Worthy, Chris McDowell, Alma, Stephanie Tapia, and Don Barker. And then we were also really lucky to be able to talk to a number of experts from Goddard, Marshall, JSC, and also from Boeing and Aerospace Corporation. Next slide, please. So here we just wanted to list a number of resources that might be interesting for people that are working on this topic. So for an example, we have the SLS Spec 159. We have a meteoroid engineering model, outgassing nasa.gov. One really useful resource is the MAPTIS, where you can find a lot of materials information for testing that's been done. And then there's also a really great wiki for lunar dust testing. And then finally, there's several test facilities within NASA that can do, like, for example, solar wind testing, UV testing, or lunar dust testing. Next slide, please. So finally, this is just our, so finally, this is just our list of references. So this includes the references for the different figures. It also includes references for data that we found helpful. We have many, many more references that we've come across just as we've been studying the literature. So if this is something that you're interested in learning about further, definitely contact us for more information on a particular topic. Another thing I'd like to just note is that Abby mentioned this is an ongoing project and we're all, learning about this topic as we go along. So if this is something that you're working on or have experience in a particular thing, we would definitely love to hear from you. So this concludes the presentation portion of the short course, and we'd be happy to answer any questions.
So I think I see one in here asking about so the measures must be taken in vacuum to be more accurate. How is this done? So I think you're talking about the UV testing that we had talked about. So it's important to take these measurements for optical properties in vacuum because when they're exposed to oxygen, that can very, very quickly change the optical properties again. So how is this done? This has to be taken into account with the test setup that you have. So your chamber that you're testing in your vacuum chamber, you have to be able to measure the emissivity and absorptivity in vacuum in the chamber without opening it up and taking the measurement there. So that is just depending on where you do your testing. Next. Is the GSFC estimated EOL after all those degrading effects and uncertainties available to the public? Not yet. This method that we use, I think that is available to the public. This method that we show right here, you can use this. This chart will be available through just a basic Google search if you Google the title eventually. Hopefully within this week, we'll have that available. So you can search for it. As far as the end-of-life property estimates for NRHO, we're working on that right now still. So it's not available to the public. It will be available to anybody working on Gateway once we release our thermal data book. And we'll keep working on that. Astroquartz causes RF interference. Do any other materials you discuss interfere with RF? That is a good question. There are probably a few that do, and that would be one of those extra requirements that Sydney was talking about that you would have to take into account when choosing your material. So I didn't have that in this presentation, but that's a good thing to note. So thanks for bringing it up. Ooh, awesome. Help for discussing MLI. I would love to. Is iodine conversion coating on aluminum okay to be used on exterior surfaces that are exposed to AO, radiation, etc.? Let's see, let's go back to that chart. Here it is. So iodine, that's this guy right here. So it does protect against corrosion. I believe it is resistant to atomic oxygen, and things of that nature. So I'd say it's probably on the same lines as anodized aluminum with resistance to degradation like that. There is the problem that it's not scratch resistant. So if you do have scratches, they will be exposed. And I think that's probably something to do with the actual thickness of the layer. So anodized aluminum has a pretty thick layer. So even if you scratch it, it's a layer of aluminum oxide. Even if you scratch it, you're still getting to more aluminum oxide. So you're very resistant to things no matter what. However, with the iodine coating, it's thinner. So if you scratch it, you have the bare aluminum that will be exposed to the environment, which can have some more severe effects. Obviously, if it is exposed to atomic oxygen, it's going to react and turn into aluminum oxide. So there's that. It depends on what material properties you need. So yeah, that's it. Any other questions? Yeah, thanks a lot for listening, everybody. And again, if you have questions that we didn't get to answer, you can send us an email. We have our emails at the top here. So I'll just show that. So yeah, you can let us know. And also, if you have experience that you'd like to share with us, we'd love to hear from you. Same, shoot us an email. So that's it. I think we're done.
All right, thanks everybody for tuning in. Yeah, I hope everyone makes it to their next session that they want to join. I'd like to thank the presenters again for a great short course, and yeah, we'll see you all soon.